All right, this video is on PES, or photoelectron spectroscopy, and how it relates to ionization energy. All right, so as a quick recap, we've just spent time learning all about ionization energy, or abbreviated IE, which is, of course, the energy needed to remove an electron. And so we spent a long time talking about how that's related to ZEF and lots of other topics. But the big takeaway point, at least for PES, is this idea right here that says that the ionization energy of a core electron is much, much greater than that of the ionization energy of a valence electron. We've talked about that in terms of the core electrons are not shielded as much, where the valence electrons are shielded. And so, bottom line, big takeaway point, it takes a whole lot more energy to remove a core electron than it does to remove a valence electron. So keeping that in mind, and keeping in mind that sometimes the ionization energy is often referred to as the binding energy, because it's what binds the electron to the nucleus. That's kind of just another name for ionization energy, and that seems to come up a lot in this discussion of PES, or photoelectron spectroscopy. So what is PES? So basically, several years ago, there was a big push in the AP curriculum to teach this idea of PES graphs. And if I had to define PES for you, which is the next heading on your paper, what is a PES spectrum? I would say that it's an electron configuration and ionization energy graphical representation. Okay, that's exactly what it is. It's pretty much the combination of an electron configuration, like 1s1 or 1s2, 2s2, and so on and so forth, and the ionization energies associated with each of those electrons in those orbitals. So, pretty much, give or take, all PES graphs look very similar. And so this is an example of a PES graph. If you notice your axes labels, the y-axis is always the number of electrons, and the x-axis is always the binding energy. Keep in mind, that's another word for ionization energy. Okay, so one thing you'll notice very quickly about this graph is that it seems to start kind of backwards on the x-axis. If you notice, it starts with a big binding energy of 100 and works its way down to 10, 5, and then down into the one-ish amount. And so this seems kind of backwards to us when we normally start a graph at 0 and increase our x-axis. So it's just something to be aware of. Most PES graphs do this, some don't, and we'll talk about that in a minute. Okay, so basically this is a graph of number of electrons and their binding energy. So if you think about what we talked about up top just for a second, that the ionization energy, or the binding energy of the core electrons, is always much larger than the valence, then we should quickly be able to establish which end of this graph is the core and which end is the valence based on the binding energy. So obviously core ionization energies are larger than valence, so the largest binding energy, these are going to be my core electrons. Okay, so that's always what I do first, is kind of figure out my orientation and figure out where are my core and where are my valence. And again, I know that because the core electrons are going to be the highest energy to remove, and the valence electrons are going to be the lowest energy to remove. So I've now established that this is the core, it's kind of side of my graph, and this is the valence side. And so the way PES works is the first peak is representative of the 1s atomic orbital. Knowing that that's the 1s, and knowing that most likely the 1s is full, this peak here would be representing 2 electrons. Keep in mind the y-axis is marked so that this peak, okay, is representing the number of electrons. In this case, it's going to be 2, and we know that because the 1s orbital is full. Now, notice, your energy decreases quite a bit because, of course, the next set of electrons, the 2s, would be much easier to remove than the 1s. And so my next peak is pretty much of equal height to my first peak, and that's because it also represents 2 electrons, and that is the 2s orbital peak. Okay, so the second peak is representing the 2s electrons. Of course, there are 2 of them. And I just keep going like this with electron configuration. So of course next comes 2p, slightly less energy to remove those. And here, sometimes you kind of have to eyeball this But this is definitely higher than 2, and you know, if you kind of eyeballed, it's double would be about there, and so it seems to be about triple. So this peak is triple the height of this peak, meaning if this peak represents 2 and this peak is triple, this must be representing 6 electrons, which of course should make sense for us because we know the 2p holds 6 electrons. Continuing that same pattern, next comes the 3s with 2 electrons, and again, look, that peak is pretty much, give or take, my lines aren't perfectly straight here, I apologize, pretty much in line with my peak for my 2s and my 1s, again representing 2 electrons. And then of course my last peak on here is the 3p, that's my next orbital, and this is where sometimes we have to estimate just a little bit. Obviously this third peak is higher than the 3s peak, and so it must represent more than 2 electrons. If it only represented 2, my 2 peaks would be equal. And kind of eyeballing this, I personally don't think it's double, and so double of course would be 4 electrons, so I'm going to say I'm pretty confident that this last peak is representing 3 electrons, in the 3p orbital, okay? So from there, because we now have an electron configuration, 1s2, 2s2, 2p6, 3s2, 3p3, we can very easily identify this, this atom. So very quickly, shoot, I don't have a different color marker, so I'll just still stick with blue. So these are, of course, my core, right? My 1s and my 2s energy level electrons, and then my highest energy level, in this case being 3, this would be my valence. Okay, so 5 valence, 10 core, 15 total electrons, and I believe that's phosphorus, I think. I don't have a periodic table with me. I'm pretty sure element 15 is phosphorus. And so I can identify an element based on the PES graph, okay? And I can pretty much do that for any, any graphical representation of this, pretty much keeping in mind that I'm always going to think about where I am on my graph, okay? The high energy versus the low energy, the core versus the valence, and then basically it's a graphical representation of electron configurations, and that's all PES is. It seems slightly more complicated than what it really is in looking at the graph. Now, if you flip your paper over, I'm gonna try to get this to focus. Yeah, I'll try. There are 2 other different types of PES graphs. If you look at the top one, it looks very similar to what we just saw. The main difference, though, is look at your x-axis. Okay, your x-axis is going in what we would perceive as the normal way from small to big. So you would just have to get your orientation correct. Again, meaning if this is the smallest energy, the lowest energy to remove an electron, these are my valence this time, and my high energy, lots of energy needed to remove an electron, that must be my core. So in this back graph, here's my my 1s orbital. Again, my peak is 2 lines tall, 1s2, 2s2, 2p6. If you notice, this peak is 3 times as tall as my 2s, goes up to line 6. So 1s2, 2s2, 2p6, 3s2, 3p1, it's half the height of this one, and that must be the PES for aluminum. So it's the same idea, it's just that in this case my x-axis was backwards to what we learned the first time. I will tell you, most of the time your PES graphs are going to be high energy to low energy, but that's not always the case. So you must be aware of the units, so to speak. Well, not units, but the way the x-axis is drawn on your graph. Okay, you must always look at that. Now, the third type, which is hardly ever shown, at least on an AP test, but it could, I guess it could come up. It's almost like a double graph. And again, it takes a minute to look at this, but again, you're looking for high energy versus low energy. And so if you kind of check this out, here's 10, I think it says MJ, that's megajoules, but anyway, so 10, here's 0. And then if you kind of follow the second graph is 10 to 100. So here's 100, here's 10, and then it's like the graph kind of starts over again, going from 10 down to 0. Again, keeping in mind, you're just finding where are my high energy electrons, where are my low energy electrons to get your core and valence in the right place. So here, of course, it's even labeled 56.2 is the exact energy value. That's my highest energy electron. It's even telling you there's 2 of them. This is the 1s. 1s representing 2 electrons. Again, the next one, the next highest in energy is this one, which is the 2s, representing 2 electrons. And then the 2p representing, again, they're telling you 4 electrons, 1s2, 2s2, 2p4. And that would be oxygen. And so I can identify, again, even though this graph looks a little odd, I can still identify an element based on their PES graph. Now, there's a bit more to PES in terms of what if we graphed 2 of them on the same graph? How would that look different? How would ions look? In terms of the PES for sulfur versus the PES for sulfur -2, and that's all types of things we're going to discuss in class.